So it feels like we're hearing about some crazy new AI breakthrough pretty much every single day, right? But behind all that hype, there's this one giant, really critical question. How do we actually know that any of this stuff is going to work safely and reliably out here, in the real world? Let's get into it.
I mean, think about it. When we're talking about something like a self-driving car, you can't just, cross your fingers and hope it all works out. No way. We've got to be confident that it's safe before it ever hits the road with us on it. This isn't just some abstract idea, right? This is about our safety, our trust in the tech that is literally changing everything around us. And this right here, this visualizes the problem perfectly. So over on the left, you've got the development stage. Think of it like a nice, clean laboratory. It's a totally controlled environment where we train and test the AI on a neat, limited set of data. But then you look at the right side. That's the deployment stage. That's the real world. And the real world, it's messy, it's unpredictable, it's infinitely more complex. There's this massive gap between the two. And that gap, well, that's where all the risk is hiding. Okay, so this brings us to two really important concepts. See the magnifying glass on the left? That's what we can actually measure in our lab. The error rate we find there, that's called the test error. But then you have everything else, the entire unpredictable world on the right. The actual error rate out there, that's the true risk. And that's the one that really, really matters. The problem is, our test error is the only clue we have to figure it out. It's like we're detectives with just one piece of evidence. So, how in the world do we take that one tiny clue and solve the huge mystery of the true risk? Well, to figure that out, we're going to have to do something a little weird. We're going to forget all about complicated AI for a second and look at something way, way simpler. Yep, a standard six-sided die. I know, it seems like it has absolutely nothing to do with this, right? But here's the crazy part. The math that governs this super simple roll of a die, it's the exact same math that lets us build trust in a super complex AI. Stick with me here.
Now, with a simple die, we have a huge advantage, a luxury we just don't get with AI. We can actually calculate the true answer. So if you could somehow roll this die an infinite number of times, the average of every simple one of those rolls would land exactly on 3.5. We call this the expected value. Think of it as the ultimate ground truth we're trying to pin down.
But okay, obviously we can't roll a die an infinite number of times. That's impossible. We can only roll it a limited number of times, right? Maybe 100 or 1,000. The average of those rolls, that's our sample mean. It's our best guess, our estimate of that true value of 3.5. And it's based on the limited data we have, just like in AI's test results. Okay, now this is where it gets really cool. Watch what happens as we start rolling the die more and more. See those lines? At the beginning, they're jumping all over the place, just total chaos. But as we increase the number of rolls along the bottom, as our sample size gets bigger, look what happens. All three lines start to calm down. They begin to converge, getting closer and closer to that dotted line, our true expected value of 3.5. And this amazing thing we're seeing, it's not a fluke, it's not a coincidence. It's one of the most fundamental principles in all of statistics. It's called the law of large numbers. And all it says is that the more times you do something, the more trials you run, the closer your average result is going to get to the true expected value. The takeaway is simple but so powerful. More data gets you closer to the truth. So what does all this mean for how confident we can be? Well, take a look at the bell curve on the left. What it's telling us is that even if our average from just a few rolls is a little bit off, it's most likely going to be pretty darn close to the true value. Now, check out the graph on the right. This is even more powerful. It shows that as our number of rolls goes up, that's the axis on the bottom, the probability of our guess being way off just plummets. It drops like a rock. More data literally crushes the chances of making a big mistake. And again, this isn't just something that tends to happen. It is a mathematical guarantee. There's this thing called Hoffending's inequality. Now, we're not going to get bogged down in the formula, don't worry. But what you need to know is that it gives us a hard mathematical upper limit, a ceiling, on the probability that our measured average is way off from the true one. You can almost think of it as a statistical stamp of approval. All right, so we've rolled a bunch of dice. We've seen the law of large numbers in action. It gives us confidence in our average. But how does this simple game of chance get us back to solving that huge high-stakes problem of trusting an AI? This is the big reveal. This is how it all connects. Just like with the dice, we have that true risk, the real-world AI performance that we can't see directly. But what we can see is our test error. That's just the average error on our limited test data. And here's how to think about it. Every time the AI makes a mistake on a test, let's call that a 1. And when it gets something right, let's call that a 0. Our test error is literally just the average of all those 1s and 0s. And what's the bridge between what we can see and what's true? Look at the bottom. It's the law of large numbers. It's the very same engine that connects them.
So let's just spell it out, make the connection crystal clear. The sample mean we calculated from our dice rolls, that's the exact same idea as the test error of an AI. And the expected value, that true hidden average of 3.5, that's our AI's true risk in the wild. It's the same logic, just applied to a different problem.
Okay, so what does this give us in practice? What's the payoff? We still can't know the true risk with perfect pinpoint accuracy, but we can use our test error and the power of the law of large numbers to calculate something called a confidence interval. And what that is, it's a range of values where we can be really, really confident that the true real-world error rate is actually hiding.
So, for example, after running a whole bunch of tests, we could calculate a, say, 95% confidence interval. And that lets us say something incredibly powerful. We could say, okay, we are 95% confident that the true error rate of this AI out in the real world is somewhere between 1% and 3%. See? We don't get one single magic number, but what we do get is a reliable range and a precise number for how certain we are about it.
All right, let's just quickly wrap up the key takeaways here. Number 1, the law of large numbers. That's the bridge. It's what connects our test results to the real-world truth. Number 2, the more test data you have, the better your approximation gets. It's that simple. And finally, all of this lets us create confidence intervals. And that is a real, practical, mathematical tool we can use to put a number on just how much we can trust an AI.
And that brings us all the way back to the beginning. So, the next time you see some big headline about a new, world-changing AI, you now know the single most important question you need to ask. How did they test it? How much data did they use? Because now you know the answer to that question. That's the entire mathematical foundation for whether we can truly, actually trust it.